Morning, everyone. It's been early, I guess. So today will be my last lecture about using machine learning for high energy physics. It will also be the lecture which contains the most applications. So it's mainly focused on how can we actually use all those ingredients I gave you in the last days, like using normalizing flows from yesterday, using classification you heard also from Yong-Hoon on Monday. How do you use these things to actually do machine learning at LHC searches? So what it's going to today be about is about anomaly detection and hunting new physics at the LHC. So yesterday you already heard a bit about anomaly detection from Tillman. Parts of what he did, or everything he did, I will also repeat. So this should be kind of something familiar to you. But I try to give first a little bit more of a introduction about what anomaly detection is about in its core and why we care and why we think it might be relevant. So let's get to the last point. Anomaly detection. And let me start first with some basics. So whenever we usually consider trying to find new physics at the LHC, everything is usually supervised, which means we have our conventional LHC search basically is we have some model, we calculate, do simulations with it, and we compare this to data. And this worked very, very well in the past. We did this for 20, 30, 40, 50 years. But now, since after the Higgs discovery, we're now in an era where we know, well, everything we were hoping to see, like supersymmetric particles, deep dark matter, anything like that, has not been found yet, which doesn't mean it's not there. It's definitely there out there, but we right now don't have, let's say, my point of view, a really good model out there to describe it. So what can we do about it? I mean, of course, there are a bunch of models. You can think about a lot of them. In principle, we can keep on simulating all of these and constantly compare everything. But this is very inefficient in this vast amount of possibilities. So what people are thinking, we need to have something like a model-independent search. And there are not so many out there. It's like just a part. And most of the stuff we're doing is like the conventional, supervised searching for new physics, which I would call the bread and butter of LHC physics, because that's our daily business. And that's, I don't know, probably 98% of what we're doing, at least in the past. But for the small independent searches, as it's not been done so often, and it still requires the questions, how do we do this? And this really has a great opportunity for machine learning. While in the beginning, this was mainly driven by theory people, even though you would expect, well, I'm looking for new physics and in data, you would rather expect this should have been driven by experimentalists. And I would agree on that. However, they were so busy, which of course makes sense with a lot of data and all of stuff, just doing their usual stuff, that there was just no time to think about, let's say, over the edge. So this was mainly driven in the past by theory, I would say. Nowadays, there's also a huge interest, luckily, by the experimentalists now. And as it turned out from this year's LHCb conference in Serbia, people are actually now working on this stuff, even on Atlas CMS. So they're actually now looking into this, which is really, really cool. Before we can look into typical examples, we first have to ask and answer the question, what do I mean by anomaly detection? And typically you consider two types of anomaly detection, I would say. The first I consider, I would call outlier detection. This means that you assume you have an event somewhere where you typically don't expect anything. So your naive assumption is that the probability of your whatever your background is should be 0, even though you measure something. Of course, in practice, it's technically never really 0 because there's always some likelihood to measure something. But at least say the background is very, very small. Okay? So whenever you measure something there which is unexpected, it's an outlier. This must be some hint of new physics. However, this is kind of non-trivial for two reasons. First of all, finding these regions. And second of all, a little remember of yesterday when we talked about normalizing flows. The key formula in the derivation of normalizing flows when using invertible mappings is based on coordinate transformations, which was that probabilities are conserved. So if I have a probability P of X in some volume and I do some coordinate transformation, this has to be conserved under coordinate transformation. Okay? This means if I have some background in this parameterization, which might be small in terms of P, considering some coordinate transformation, this might change drastically. Because only the entire thing has to be conserved, right? Plus times the volume. So even this can be small, this could be big, depending on how you choose your coordinate system. Which means this statement here is highly non-coordinate invariant. And there's also been a paper about this by Ben Nachman, David Shee, and Gregor about this, to take care of this when you do anomaly searches. It's quite recent, I would say. It's from last year, September. And they exactly discussed this problem. The second kind of anomaly I consider are so-called overdensities. What do I mean by this? I mean, let's assume you have some, let's say, standard model background, which is not necessarily small, but then your new physics will give you some access which might be not very big, and we assume it can't be big because otherwise you probably have found it. So it must be some very, very subtle overdensity, which means how can we measure this? And this comes under the idea of the, as I already said yesterday, I think, the Nyman-Pearson lemma. So we need to have the log likelihood ratio of our data with respect to the assumed background. And you can show mathematically that this is kind of the optimal hypothesis test for data versus background. So that's actually very important. And in a way, if you would be able to have a perfect parameterization of P data and P background, then this would be the optimal anomaly detection tests. So what we call this thing, assuming we know this, is the so-called idealized anomaly detector. Of course, in a perfect world, let's say we don't live in a perfect world, so we need to find a way how we can extract this information. And this is the reason why we need machine learning, because with standard techniques, it's quite difficult to extract both p-data and p-bug background. Of course, p-background you might be able to simulate, and we're going to talk about this, but p-data is something you measure, so how do you get that? But now it's assuming you have this information, you need some kind of, let's say, anomaly score telling you how do I find regions in where I have more interesting stuff than background. So you want to have a region in where R is big. So an interesting thing is to define some region R where R is bigger than whatever, some threshold C, and this should be bigger 1. And based on this, you use this as a discrimination variable to cut your measured data, and then hopefully have better data to extract actual new physics. That is the basic idea. Are there questions about that? It's coordinate dependent because it also has x in it. Exactly. So let me go into the first example, which is essentially a repetition of what Tillman presented yesterday, is how we can use autoencoders for outlier detection. Even though I already introduced autoencoders, just as a little reminder, what you do is you have some input which you try to map on some compressed latent space Z, and then decompress with some decoder where you have some map from X to Z and back to X. And as I already said, you try to learn this mapping, which cannot be an identity map because of this decompression step. And as I said already yesterday, in the end, you have some loss function, which is essentially just a mean squared error of your input and your autoencoder of that input. And then the idea is, that's what also Tillman presented yesterday, that this thing, which is essentially the error of the reconstruction error, you will use as an anomaly score. So the bigger the reconstruction error is, assuming you feed it with data that has not been seen for training, you can base your anomaly search. So how can we imagine this? So let's assume we have this plot where we have the reconstruction error on the x-axis, and here we have counts. And we have trained this thing on some background data. And what we hope to see is something like this, or it can even be peaked at some point. But then on the other side, if you now feed it with data that has not been seen, you hopefully would expect that this peaks somewhere at the high reconstruction error side. And then based on this, you decide where to pick or where to cut. So now you can say, well, I picked this as a cutting criterion. So I say everything where the loss is bigger than this must be interesting stuff. And I use this to cut on my data set. And I use then L is as anomaly score. For L bigger LC. And then we can use this to cut for interesting events. And this has been done actually in the past, quite around the same time, first by Timmer and Blaine and Heimel et al. In 2018. And then it's kind of the same time also by David Shee and his students. And what they were interested in particular, where they tried to detect either top jets or some Gluino jets versus some kind of, let's say, boring QCD jets. This was the idea. So they trained on QCD jets as background and tried to identify top jets or Gluino jets. Now, the problem with this is, as already Tilma mentioned out yesterday, this works quite nicely if you train on QCD jets which are very, very simple, but it breaks the moment you train on this side and try to identify QCD jets, which is exactly the complexity problem he mentioned yesterday. And of course, on one side, there's this theoretical basis about solving this with a normalized autoencoder where the main author is sitting in the audience, and then the physical application for this was then done last year by Dylan et al. Which alleviates this problem. Okay? So the general pro of this approach is that it works fully unsupervised. So I really don't have to put any kind of knowledge into it. And the cons is kind of, yeah, they're generally not super sensitive, but this is still something in discussion because this might be alleviated by using this normalized autoencoders, but that's at least a general statement. So the sensitivity might be an issue. And how to control them. But let me put this a bit in brackets, because these statements were mainly given for the unregularized, the unnormalized autoencoders. So this is something which still needs to be checked, and we're currently actually in discussion with experimentalists to actually test the normalized autoencoder in a more proper way to see how they perform. Okay. Now, the next thing I want to talk about are overdensities. Here, as I already said, what we try to learn is this R, which is the ratio of some data over some background. There are in principle, let's say, two ways to approach that. The P data is something, because it's data in it means you have no way around it, but you have to approximate or get that from your data. While for the background, you have two options. The first option is you estimate your background data from Monte Carlo simulations. So you essentially just assume your standard model, you simulate that, and this is where you extract P background from. And then what you can do, you train a classifier between your simulated data from the Monte Carlo and your data to get R, because that's what we learned on Tuesday, that you can use a classifier to learn this ratio here. If you remember that, when we defined the classifier metric, that an optimal classifier learns P data over P data plus P background. So obviously, if you reshuffle this formula a little bit, R is given by 1 minus C over C. Okay, so then you can actually learn this. So data was MC with a classifier. From this, we get R. And then based on this, we can, as I already said, cut. Okay? So what is happening there is then from this cut, you're left with some number of events. But these number of events can now be interpreted in two ways. First of all, this could be actual anomalies you have not been modeled, or, and that's what will probably happen most of the time, this will tell you where the Monte Carlo was not correct or not accurate enough. So in the end, this will only tell you all defects of your Monte Carlo simulation in modeling the background, which is not necessarily what we want. Okay. However, on the other side, if we not consider anomaly detection, we can use the same method to improve event generation, right? So if we don't have, again, where we're not allowed to train a classifier to optimality, but we allow just some external classifier to be trained on your generative data and some truth which you have under control, and allow the classifier to be trained to optimal, you can use this information to actually improve your generation by reweighting. So you can use this to improve Monte Carlo. And there are actually, in May, 2 papers out of actually making use of this. One was by Timmer and Plain, David Shee, which actually used these classifier information as a weight to reweight their generative models. In this case, they didn't reweight Monte Carlo, but in a sense, you can do the same thing. So let me call this the Plain et al. One. And 2 weeks before that, Ben Nachman and me did a similar thing where we also used this weights to improve our classifier, to improve our generative model. But in contrast to just reweights on the feature space, we used this weight information, back-propagated this into the latent space, and then used these weights to either do rejection sampling on the latent space or do some Markov chain Monte Carlo to then get also better samples. So we use this in order to get a better latent space, and this comes out of the name of ELSA, which stands for Enhanced Latent Spaces. which also makes use of using classifiers to improve. Generative modeling. Okay. So these are two techniques where, even though that's not very something you want to do for anomaly detection, this might be useful to actually improve event generation. And people have not been discussed that so much in the past, so that's why this has been current work also, and people try to make community aware of this. Okay. So then the question, the question is, if this is not a sensible thing to do, what else can we do? Of course, the only other possibility, if we cannot extract it from simulation, we have to extract it from data, right? But how do we do this? The problem is, obviously, if we extract both, where we expect something interesting from the data in the background, we need to be careful because things are mixed. So what you usually do is you try to identify for your anomaly search regions and where you expect your signal, and other regions where we find the tails to have no signal or no new physics. So you identify one region, which you call control region or sideband. You see both words in the literature. Let me call it for here just control region CR. And how do you define this? So that's a region in the data where you expect essentially just background, which means just nothing very interesting. Note that there's this approximate, right? There could be still some signal, but you assume that the amount of signal there is very, very small. On the other side, you have some signal region. Let's call it P data as signal region, which then is approximately P signal. But then, of course, if you want to be a little bit more consistent about normalization of everything, you probably put something like this in front of that, meaning you want that epsilon is close to 1. Okay. But of course, in always you kind of have a mixture, and the same would be true here. And then the idea is now use a classifier to learn R between signal region and control region. To learn R. And you might now naively think, well, but I have mixed samples now, so how does it help me? But that's not a problem, actually, because you can mathematically prove that even if you have mixed samples and you just do this step by step, that the R you get out of this classification is just proportional to the true R you're interested in. So it's perfectly fine to do this classification on mixed samples here. And this comes under the name of classification without labels. But because this is a very, very long thing to always say, and because physicists, especially in the US, are very creative, this entire thing is called koala. Like the animal. Yes?
So you don't give a specific label, but you do identify control region and signal region.
Yes.
So that can be, actually that plays a role of the label, no?
Yeah, well, I mean, but it's a mixed label in a way because you
It
only
is
have
a mixed label,
sample. Yeah.
right? But you do know that actually there is a background only control region.
Yeah.
So it's a, I don't know. Yeah, I mean, it sounds like it is a label to me, but
yeah, you should. Yeah.
I understand that there is no specific label for signal.
Yeah, yeah.
Another question is,
I mean, I didn't invent the word.
right,
I
of course,
agree
yeah.
to you, it's not completely unlabeled, but it's also not clear that this is 100% just signal. You have a mix.
Right.
So in a way, you just know in this mix is proportionally probably more signal than background, but you don't have a, I mean, it's still true because you don't have a clear label of the individual samples in the set. You just
Right.
have an idea of the entire data set.
Right. Yeah. Yeah. That in that sense, that is true. So, is this similar to somehow, I don't know, machine learning version of a sideband subtraction? Right. This is exactly what you do in the sideband subtraction, right?
Yeah, yeah. Probably.
Okay.
Yeah.
Yeah.
And this idea has been invented by Ben Nachman and Jesse Taylor and one of the students in 2017. Like just this method that this classification is as strong as doing the classification on the proper. You have a question? Okay, so you just have to push it up.
Hello.
Yeah, it works.
How do you decide the signal region? Does this bring any bias, like model dependence? If you choose a phase space, for example, you assume that there's a signal, right? So does this bring any model dependence to your ansatz?
Yeah. It will. I will go into some examples and then become clear, I guess. And then the first attempt of using this for anomaly detection was in 2018, also from Ben Nachman, Collins, Howell. Okay. And this thing, as Casey already pointed out, is not fully unsupervised. So you need a bit of supervision because you need to identify in a way from outside what is your control region, what is your signal region. This is also denoted as weak supervision. And of course, this weak supervision comes with a bias, naturally, because you make an assumption that in a signal region, you assume there's no signal, which exactly comes to the point of what Jack just asked. There is intrinsically now, you have some model independence in it, but at least it's not as strong as if you have to calculate everything. And of course, this entire thing only works if, as I pointed out, the signal is supposed to be small, otherwise it breaks. But on the other hand, I think we know the signal has to be small because if it would not be small, we've already found it. So I think that's a fair assumption. Okay.
Can I have a question?
Sure.
So, so you said that so you can improve the MC with, using classifier. In the sense of the event generated looks good, but in the sense of anomaly detection, it sounds a bit dangerous because it might also mimic the anomalies. I mean, if you can classify, I mean, if data have anomalies, then generator might mimic the anomalies, right? There is no problem.
Yeah. You mean if you use this to improve the generative model, you mean, or what? I saw the question, as far as I understand it, is, isn't it dangerous to use this classifier to improve your Monte Carlo because maybe you're correcting for anomalies in it? It would be true if you would correct the Monte Carlo with something you don't know. So you there also have to be careful about some control region where you know what's going on. Or if your generative model is a machine learning model, you're corrective with respect to some super, super slow, but very precise standard Monte Carlo where you know what's going on. And so you compare it with a Monte Carlo there. So you just try to improve the fast generator essentially. And then you're not biased because in your controlled but slow standard Monte Carlo, you know there is no anomaly in because that's how you construct it. And you just use the information to correct your fast simulation. Okay. The next thing I want to talk about based on this is generally referred to as koala hunting. It sounds very dangerous, but we are not killing any animals. So this tries to make clear a little bit more how this works in practice. So let's assume you have some process with some invariant mass, for instance, you're interested in, and you have some background. And somewhere in this background, you have some bump. It might be very subtle, but let me exaggerate it, otherwise you cannot see it. Let's assume you have something like this. And then, of course, you could call this the signal region and those outer sides the control regions. Okay? Of course, what you can do in practice is like saying, well, in practice, I don't know where the signal region is, but then I can just scan over this parameter space. So I can like start at some region, let's say, have a window of 20 GeV, and then I scan over it, right? So now, in practice, let's, for instance, what they did is you have, for instance, some Z prime, which decays into some X and Y, which are not that heavy, and they further decay into some quarks. That's some signal, but that's much heavier than MX and Y, and that's actually part of the LHC Olympics data set. So you actually, you know the drill. You have here some very long jets. And what I want to tell you is that, of course, while this is an interesting variable, you have much more features to learn from than just this MJJ, which gives you the Z prime thing. So often it's useful, also for anomaly detection, to use as much information as possible. So you also can, for instance, try to use MX, MY, MX, or for instance, some chattiness variables, etc. The only problem is these additional parameters, they might help you, but let's denote all of this as some variables X. This X has to be carefully chosen. Because the problem is, the moment these parameters are highly correlated with MJJ, you might do something wrong. Because these parameters have to be independent of MJJ in the background, because otherwise this doesn't work out. So with carefully chosen, I mean this has to be independent of MJJ in the background. But on the other hand, you want to use more variables, because let's assume you just use one variable. It might be possible that you have a significance of measuring a signal. Let's write it down 1 dim, or just using MJJ. It might be possible you have a significance of 1 sigma with this method. But then by using more information, because of course you're in a high dimensional hypersphere, if you use X, you might reach 5 sigma. So you can get a huge improvement in the likelihood of measuring a new signal here. But again, the problem is I need to be careful on how I choose these x's, which means in practice, which means in practice that I really have to be careful, and I have not such a huge possibility of picking x if at least just try to think about it with my brain, which means on average I don't get so much sensitivity because I cannot use so much more information. So what can we do about that? Then people had an idea about doing this differently. And this comes into play about what we learned yesterday, that normalizing flows cannot just be used to generate data, they can also be used to learn probabilities. So what people were trying to do, instead of doing this learning such a classifier only, we have this ratio which we want to learn, use the normalizing flow to learn these P data and P background directly. Okay? This comes under the idea of anomaly detection through density estimation, or short ANOD, which has been done in 2020 by Ben Nachman, David Shee, and their collaborators. So there they say, let's train a density estimator, which was just a normalizing flow, and then use this density estimator trained on a control region. So they tried to learn P data of X, where X are all variables they would like to put in. And now this is an important thing, conditional on the interesting variable, which is MJJ. In the signal region, so they still do the split in signal regions and control regions, and they learn P data X MJJ in control region. And then the nice thing is, because this is only trained in the control region, but conditional MJJ, you can extrapolate, let's say, P background into the signal region by essentially putting in the MJJ of your signal region. So you get an expectation, an estimate of your background in your signal region. And the nice thing about doing it like this is, because you really learn a conditional probability, all correlations which might be there are learned. So you don't get any problems. And then the R is just the ratio of those two things. And a clear advantage is it's robust against correlations between X and MJJ because they are learned. So you don't have to be careful in how you choose your X. On the other side, we know very well that training a generative model or density estimator is not that trivial. So you saw yesterday that there are a lot of efforts in how you do this generative modeling, and normalizing flows are quite promising. But even though they only reach a certain precision when you do so, especially limited by data. On the other side, classification is much, much easier and gives you way better precision, which means trying to learn this P directly is less powerful in a way. Because classification is easier. So what do we do about it? And then we're like, again, the people from the anode paper and the koala hunting, they were like having a discussion about this, and I said like, well, what about combining those two ideas, which comes under the name of density anomaly detection through outer density estimation, which they called cathode. And it's also by Ben Nachman, David Shee, Gregor Kosiecka, and friends. And that's from 21, so it's 1 year later. Okay. So outer density estimation, that's what the idea is. So the idea is now combine koala with anode. So try to use the strength of both approaches. So what you do is you train a density estimator. So let me show it right, train a flow just in the control region. And then fit this to learn as before the background probability. But now the nice thing, because of a normalizing flow, is once we trained it, we don't just can calculate down the P, we can also use it to sample. So instead of directly using the P information from there, generate samples everywhere. So now you generate samples not just in the region where you've trained on, but also in the signal region. Of course, based on that assumption that it was background. Why do we do this? So if you carefully look into this, just this upper thing is ratios there, what you found and what you should also remember from yesterday, normalizing flows have a good quality, but they start to break the more kind of peak structures you get into it. And we assume that background in the control region is consistent, like is consistently very, very smooth. So we expect using a kernel, using a density estimator to learn the background should work sufficiently well, while the signal might be very, very rare and very, very hard to pick up because this is something very elusive. So that's complicated. So that's why we decide we don't try to learn this with a density estimator because it might be too complicated. So we only learn the background and control region, expecting a good performance, and then use this to generate samples. And now we have samples in a signal region building up on this fit. And for the signal region, the data, we have the data samples available anyways. So then we use Koala between data and background, where now these background samples are directly estimated from a control region or data set. So now we have background samples that are not from Monte Carlo, they are directly estimated from a control region. And if you do this, you kind of get best of both worlds, I would say. Okay. Before I'm going to show you and plot where Koala, anode, cathode, and also this idealized autoencoder, auto anomaly detector, because we know what's going on, are compared. I first want to explain one metric and how to compare them so that you will understand the plot. So how what's a metric in order to judge if our anomaly detector works well or not. Usually, a metric for anomaly detection, we use something which is called the significance improvement. What do I mean by that? So if we look back into this image, in the signal region, everything which is here in blue, that's our signal, and everything underneath is the background. Okay? So this bit of it is just the signal, and everything else is the background. So generally, the significance is given by S over square root of B. So the bigger this is, the better is our statistical significance of measuring this. Now the idea is using our anomaly detection technique to improve both the efficiency of our signal and also change the efficiency of measuring our background. Okay? Which means what we end up having is epsilon s over epsilon b square root. So this factor here is exactly the factor by which the significance improves. Or if we do it very, very badly, goes down. So if this is smaller than 1, we make things worse. But the hope is that the method is done in such a way that this factor is bigger than 1, so we get an improvement. Okay, before I'm going to show the plots, because then I will put down the thing you cannot see anymore, in which I will compare the different techniques. I just want to mention that, I mean, this was cathode, this was in 21. Since then, a lot of other ideas have come out to further fine-tune these methods. So let me just call it future, which is everything until last week when I prepared the lecture, essentially. There is one thing which was called curtains, which is essentially like cathode, but it's not sampling, it's trying to transport information from control region, signal region. But it's otherwise it's kind of the same. Then after that, there was, let's say, the older brother of, or let's say the next generation of cathode came out, which was called La cathode, which on purpose should sound a bit French, but it actually means doing the cathode method, but on a latent space, because as I already mentioned at the beginning, in all of the times you calculate in R, which depends on your feature space, and as it turns out, due to the fact that depending on your parameterization, this R can change quite a lot, they decided to not define R on the actual feature space, but because if you have a normalizing flow, you have invertibility between your feature space and your latent space, you can also define everything on a latent space. And it seems to work out better because you're much less dependent on how things are correlated. So that's La cathode. It's October last year. So it was kind of newly presented in a conference. And then on top of that, people were saying, well, all of these methods are purely data-based. And we kind of rejected everything with simulation because we say, well, they have some biases, they have some problems. But of course, if we are careful, we can still use the knowledge we have. I mean, we have some knowledge like how we parameterize our standard model. So if we're careful, we can still use it, right? So people were saying, okay, these data-driven techniques are good, but we can still do some simulation-assisted anomaly detection. And one of the latest one is from December last year, which was called Feta, like the cheese. Unfortunately for this one, I don't know what the acronym stands for, but I also feel like that in the anomaly detection community these days, they are trying to fight each other by finding the most fancy acronym for the method to be even more memorable. So I don't know what's coming up next. I don't know, Emmentaler, I don't know, another cheese. We will see. Thank you. So flow enhanced, which means they probably also use it for simulation. All right. Before I'm going to show you the plots for comparing QUOLA with anode and cathode, is there any question?
So most of these methods seem to rely on some kind of localized features.
Yes.
Where you can identify control region and then signal region, which is fine. So, but then does any of these methods identify which kinematic variable actually give you the localized features over the background? So for example, do I need to know the MJJ in advance? Or is this kinematic variable is a learnable thing?
Yeah. So far they're not doing that. So they always assume it's observable, and then the idea is so they always go with the observables which you would naively do for standard bump hunting, and then the idea is just in a way find a better discriminator in how to cut my events to enrich my signal amount in this observable, and then once I did this, once everything has been cutted, they just take this 1D observable again, like in standard search, do a bump hunting and do the standard stuff. So they're not doing anything fancy. But of course, in principle, there might be possibilities to combine that to identify initially better options. But in a way, I would think it's a good way to go, because in a way, even if you decide on one observable you actually want to cut, or like you want to look into it, this observable is correlated to everything else. So even if you identify a better observable, if you implicitly make sure on that observable, whatever this is, you cut on it by doing this anomaly detection search, you might still be able to enrich your signal in the one observable you predefined. So I think that that's okay.
Okay.
And the nice thing about it is why people doing it like this is very, very easy to directly combine with everything which has already been done or is happening at the LHC. Because they can just use their standard tools, the standard bump hunting. It's just about how to change the cuts of your events. And they know how to deal with cuts. So it's just like giving them a different way of cutting. So it's very easy, which makes it easy to communicate to experimentalists, because the more complicated things get, the more they actually have to, let's assume, they like to consider observables they know because they feel like they understand something. So if we now would go there and say, oh, but you should also try to learn this observable with machine learning, they would be much, much more afraid to actually use it.
Yeah, thank you.
And there they have kind of the feeling of being under control. Okay. Then I will show you the comparison. So here on the right plot, which is the important one for now, is you see the signal efficiency, which is this epsilon s I showed you. And of course, you can also plot epsilon s against epsilon b, which is on the left-hand side. But let's say for the interesting bit is epsilon s against the signal improvements. And the dotted lines is what's happening if you just randomly do something. So you see you're not really gaining anything. And then, depending on your method, you get a better or more or less good improvement. So QUOLA which was the first method, the orange one, is actually performing quite well, where of course you have to think about it a little bit more carefully about how you pick your parameters. Even though anode was from the idea maybe a bit more advanced, it actually turns out it's not performing so well just because it's very, very imprecise in modeling the data in the signal region. But then if you combine the koala with the anode ansatz and go to cathode, you get this pink line, which outperforms both and gives you significance up to 15. And the interesting thing about it, it's pretty close to the idealized anomaly detector, which is if you know what P is, which in this case was possible because it was some toy model. So it's very, very close to it. That's quite interesting. And then of course, on top of that, you could also do some supervision where you actually know where things are. Then you're even better. This nicely shows you that cathode and all these things actually work nicely. So let's assume you would just have a 1 sigma somewhere if you just do the standard methods, standard bump hunting, and then go ahead and use cathode on that thing and enrich the signal, improve the significance by a factor of 12 while you go from 1 sigma to 12 sigma, and then you would suddenly have a discovery. So that's actually quite useful. All right. This brings me to the end of my lectures. Sure.
For the normal CR package, so where exactly would you expect, like comparing with these methods?
I don't know. I don't know, actually. I mean, I know the anomaly CLR because it also was worked by Barry Dillon and friends. But it would be interesting at some point, because even now popping up also with the other stuff like theta, curtains, etc. At some point do like a proper comparison with everything. But on the other hand, things are like growing so fast that you end up have to do this comparison every year. So the best thing you can do is, instead of doing all these comparisons all the time, decide on some fixed benchmark data set you give out once and for all, and people always do the same things. So no matter when they publish things, then saying I have a signal improvements of 15, you know what they're talking about. So you don't always have to redo everything for the rest, because of course, otherwise it will also be more complicated. If I invent a new method and I always have to redo all the other methods just to compare it, then at some point it also becomes a bit cumbersome, I would say. So the best idea would be to have some common data set. There are some common data sets, but I think if people, for the proper comparison benchmark, we need to find an agreement, and there is kind of agreement on it.
Yeah, I mean, but just your intuition, would you expect to more likely this capital?
I would assume it somewhere. I would assume it to be better than koala, but I think not as good as cathodes, so somewhere in between, naively.
Okay, thank you.
Yeah. All right. What did I forget? There's one thing I should mention is Jack told me to already download his exercises to be wrapped up for his lectures. And otherwise, I think I've said everything from my side, but I will be around the entire week. So if there are any other questions coming up, please just approach me, talk to me. Thank you very much.